free body diagrams, which are just a tool to help us see if an object is under a net force. And if an object has net force, that's any object that is experiencing an unbalanced force. And an unbalanced force is any amount of force that is not equal to 0 newtons. If we have a net force of 0 newtons, we say that's a balanced force. What that lets us know is any unbalanced force is always going to cause acceleration, and any balanced force will never cause acceleration. A free body diagram is a way to break things down into simpler pieces so we can understand what's happening. Now you'll see free body diagrams that have a box in the middle. You'll see free body diagrams that have a dot. You'll see free body diagrams that are pictures of people doing activities or pictures of objects. But what's really important about the free body diagrams are these arrows. And these arrows won't always be at nice 90-degree angles like this, but for 8th grade, that's all we're going to worry about. Now, there's a couple different relationships that these arrows can have. First, there's a magnitude to these arrows, usually. If we have a little arrow, that is a little force. Now, that's relative. If we have a little arrow on a picture of planet Earth, that's probably actually a ton of newtons, but it's a little force for that. The bigger we draw the arrow, the more force that is. So a little arrow is a little bit of force, and a bigger arrow is more force. So we need to compare the size. For instance, all the arrows on this free body diagram are even, so we can assume that these forces are balancing each other out. The next relationship we can have is if arrows are pointing the same direction, we're going to call those like forces. Okay? And they're going to work together. They'll be added together. And if we have arrows that are pointing the opposite direction, we're going to call those opposite forces. There's different words for like forces, but opposite forces is pretty consistent. So first we're looking at the size of the arrow, whether the arrows are pointing the same direction or opposite directions. Now our last distinction is the arrows can also be parallel or they can be perpendicular to each other. Parallel arrows are going to interact. Parallel forces are going to interact. For instance, if you're pushing on a cart trying to push it left and I'm trying to push it right, we are going to interact with each other. If you're pushing left and I'm pushing left, we're working together because those are like forces, but we're still going to interact. If forces are perpendicular, they really don't have anything to do with each other. For instance, if gravity is pulling that cart down, that's not going to balance out the force that we're pushing on the cart with. It'll affect other things like friction, so it might look like that. But if forces are perpendicular, they don't exist to each other, and they're going to ignore them. So this force cares about this force, but these two forces really don't care about each other at all. So we're looking at these three arrow relationships no matter how the free body diagram is drawn. Whether it's a dot in the middle, whether it's a picture with arrows coming off of it, whether it's arrows in a simulation, we're looking at these three things. Do the forces interact with each other? If they're parallel, the answer is yes. Are they like forces or opposite forces? Meaning, are they going to add together, or are we going to find the difference between those forces? And do we have little forces or big forces, otherwise known as their magnitude?